You put in some nitrogen dioxide, and according to this equation, what's going to happen? Yeah, two of them are going to come together, and you're going to start to produce dinitrogen tetroxide. Okay? But since an equilibrium exists, is the flask ever, remember it's starting out brown, is it ever going to get colorless? No, right? Because you're always going to have some of this left in your flask. But there will reach a point in time where the color doesn't change anymore. So you'll get this lighter brown, you'll get to this lighter brown point where it's just going to stay like that. And that's the point in time where you've reached equilibrium. Okay? The rate of the forward reaction is equal to the rate of the reverse reaction. Okay? And so, equilibrium is what we call dynamic state, right? So when we reach equilibrium, it's not like everything just stops and their molecules are just looking at each other, right? Things are still, especially because we're in the gas phase, happening very quickly. Things are moving. Nitrogen dioxide molecules are combining and dinitrogen tetroxide molecules are coming apart. It's just happening at the same time. Every time two come together, one comes apart. There's no net change in concentration over time, but things are still reacting. It's a dynamic state. And so for a given reaction, as long as you're not changing the temperature. So we'll say at the same T, a reaction has what we call multiple equilibrium positions but only one equilibrium constant. Use capital K to represent the equilibrium constant. Okay, and so let me show you what that looks like in terms of some data. Here's our NO2-N2O4 reaction. So in the first one, we've pumped in NO2 at the start, times 0, no N2O4. Okay, so of course the nitrogen dioxide disappears as the N2O4 comes in. Okay, there could be another case, another reaction we run where we don't put any NO2 in, but we pump N2O4 in, okay? And you reach, you'll notice, a different set of equilibrium concentrations. This is what we mean by multiple equilibrium positions, okay? Or maybe you have a mixture where you start with a mixture of reactants and products, and you reach you reach a third equilibrium position. But what you'll notice is no matter the concentration of nitrogen dioxide or dinitrogen tetroxide you pump in, you get different equilibrium concentrations. We find that if we just take the ratio of products over reactants, we don't really get the same value, right? The ratio is different. But if we take the ratio of what we call the equilibrium constant, then we get a constant value, and we're doing this at 25 degrees Celsius for this set of experiments. Okay, and so the average, of course they're not all exactly the same, we're rounding a little bit here, but the average equilibrium constant for that reaction is 216. Okay, so multiple equilibrium positions, one equilibrium constant at the same temperature. So if we write the equilibrium constant expression, I'm going to use this sub C because we'll do it in terms of concentration first. It's equal to the concentration of products, so N2O4, divided by the concentration of reactants, NO2. And just to sort of stress the point here, I'm going to put a 1 superscript for N2O4, and then a 2 goes with NO2. So here in the numerator, we always have concentration of products. In the denominator, we have our concentration of reactants. And then both of them are raised to their stoichiometric coefficient. that's from the balanced chemical reaction. So you're always going to make sure that your reactions are balanced before you write the equilibrium constant expression. Okay? And so why don't you try this one? Write the equilibrium constant expression for this reaction, and then we'll go over what they mean. Write the Kc expression for that reaction. How about heterogeneous equilibrium reactions? So we've only looked at all gases. We could also look at all aqueous species. But what if we have different phases in the mixture? Okay, so something like this. Kc expression be for this reaction?
KCl3 into Cl2.
Like that?
Yes. We don't consider solid.
You don't consider solids. Sarah? We don't consider liquids either. So what do we consider?
Only gas.
Just gases? And aqueous solutions, right? So gases and aqueous solutions appear in Kc expressions. Pure liquids and pure solids do not. Okay? Does the concentration of a pure liquid and a pure solid change? No, right? You could calculate molar density from the density. And so the concentration, moles per liter of pure liquids, pure solids, does not change. So we don't put them in there. Amounts can change for sure. But concentration does not change. So only aqueous species and gases appear. So what would the Kp expression for this reaction be? Pressure of Cl2?
Yeah.
What would Kp in terms of Kc be?
That's it. Yeah,
1? How are we getting 1? So there's two ways we could get 1. One's right and the other's wrong.
0 minus minus 1.
0 minus minus 1.
1. I don't know. It's a guess.
1 minus 0. Good. Right? Only gases are considered. The way it's wrong is if you do 2 minus 1. That would also give you 1, which you luck out for this reaction, but for other reactions, not so much. Okay? So Kp in terms of Kc, delta N would be 1. All right, this is going to be important when we get to chapter 17 and we start to talk about solubility product constants. We're going to take solids, dissolve them, or try to dissolve them into solution. We did that in chapter 4. We talked about that when we did precipitation reactions. Chapter 4, we just said precipitate forms. Chapter 17, we're going to talk about solubility product constants and to what extent does the solid dissolve. Okay, so we're going to have to remember that solids do not appear in equilibrium constant expressions in chapter 17. And so we're going to have to calculate equilibrium concentrations. And so Brian now will bring up this idea of Q and reactions shifting. Okay, and so sometimes we're going to have both reactants and products present in our flask, and we're going to have to determine if the reaction's at equilibrium or not. And if it's not at equilibrium, then we're going to have to decide, well, which direction is it going to shift in order for equilibrium to be established? And so the way that we decide is by calculating Q. quotient. In terms of expression, let's use our N2H2 reaction. Q has the same expression as K, so concentration of products raised to their stoichiometric coefficients divided by concentration of reactants raised to their stoichiometric coefficients. But instead of using a set of equilibrium concentrations, you're using a set of initial concentrations. Okay? And so there's 3 scenarios when you calculate Q that you could come up with. You're going to always compare it to K. And so the first scenario you could get is you calculate Q and you find that Q is equal to K. What does that mean? You calculate Q and Q is equal to the equilibrium constant. Yeah, you're at equilibrium, right? So you didn't have a set of initial concentrations. You were actually given a set of equilibrium concentrations, reactions at equilibrium. No shift, okay? But what if you get scenario 2? You calculate Q and you find that Q is greater than K. Is the reaction at equilibrium? No, it doesn't equal K, so it's not at equilibrium. And so now you have to decide which direction is the reaction going to shift to reach equilibrium. So you have a 50-50 shot, right or left?
Right.
Who says right? Who says left? Who's like, I don't know what you're talking about.
No, I know you're talking about right.
You know what I'm talking about.
But no answers.
But you don't know the answer. Okay, that's fair. If Q is bigger than K, it has to become smaller to become K, right? So how can you make Q smaller? By increasing the magnitude of the numerator or the denominator?
Denominator.
The denominator. What's in the denominator?
Yeah.
Reactant. So when I ask you which direction is the reaction going to shift, you're going to tell me left, because that's where the reactants are, right? And so if you calculate a Q that's greater than K, the reaction will shift left to reach equilibrium. And so then, of course, if you calculate Q and you find that it's less than K, well then for equilibrium to be reached, you have to increase the magnitude of Q. You do that by making the numerator larger. The products are in the numerator, so the reaction is going to shift right. Okay? So, if I give you a reaction, or I give you a problem, and let's say you don't have any reactants at the start. I only give you concentration of products. There's no need to calculate Q because you know the reaction is going to shift in which direction. You only have products. It's going to have to shift left, right? Because to establish equilibrium, you're going to have to make some reactant. Same way if I give you a problem and I only give you concentration of reactants, it's going to have to shift right to reach equilibrium. No need to calculate Q. And so really you only need to calculate Q when you have some reactant and product present in the mixture. Okay? Any questions?